Everyone to, sorry, I'm admitting people while I'm speaking, so it's a little distracting. I want to welcome everyone to the first of the 2020 Summer Aspen Center for Physics, Heinz R. Pagel's Physics Talks. This is a series that we run every summer at the center. These are weekly events that we will be holding this summer virtually through August 20th. This is obviously a new thing for us, so please bear with us as we adjust to the new technological reality of doing these talks online. I want to thank everyone and welcome everyone. We already have over 100 participants, so that's fantastic. Before I introduce tonight's speaker, I just want to let you know, if you did not receive an email or would like more information about this series, you can visit the Aspen Center for Physics website, which is aspenphys, aspenphy.org. And you can also contact the Physics Center to be added to the mailing list. And these summer talks will be held every Thursday at 5:30 p.m. Mountain Daylight Time, and they will be posted shortly after on YouTube. I want to say, before I introduce Andre, our tonight's speaker, I just want to say a little bit about the Aspen Center for Physics for those of you who may not be familiar with it. The center is really a unique institution in the world of theoretical physics, and is really an important institution in the lives of our community. Every summer, over a 16-week period, over 500 leading scientists from around the world converge on the center for workshops, for independent research, and for work in small groups. This has often led to breakthroughs in theoretical physics over the time span of the center, which is now approaching 60 years. And it's really a special place where scientists liberated from their normal obligations at their home institutions can come together and just relax, interact, and think great thoughts in the gorgeous mountain scenery of Aspen, Colorado. So it's really a special place, and really is a unique institution in the world of theoretical physics. Obviously, this summer is different. For the first time, at least in my memory, the Physics Center is not hosting workshops and visitors this summer due to the COVID-19 situation. We had to cancel all of our complete summer session this year, but these lectures are an important part of our mission, and so we felt very strongly that we wanted to continue with these public lectures, and we also are continuing with our weekly colloquium series for physicists. With that background, before I introduce tonight's speaker, I just want to let you know that next Thursday's speaker will be Peter Armitage, and his topic will be Macrocosm in the Microcosm, Analogies Between Materials and Particle Physics. So I invite you to join us for that as well. I maybe should have mentioned at the outset that my name is Josh Freeman. I'm a physicist at Fermilab and the University of Chicago, and I'm currently the president of the Aspen Center for Physics. I want to introduce tonight's speaker, Professor Andre de Gouvêa from Northwestern University. Andre is a well-known particle physicist studying theories of elementary particles. He received his bachelor's and master's degrees at the Pontificia Universidade Católica do Rio de Janeiro, in Brazil, and then got his PhD in physics from the University of California at Berkeley. And as I mentioned, he's really one of the world's leaders in theoretical high energy physics, more specifically in the phenomenology of physics beyond what we call the standard model of particle physics. And so tonight he's going to tell us about particle physics, what we know, we don't know. And before turning it over to Andrea, I just want to ask people to please hold questions until the end of the talk. And at that, please keep yourself muted. And at the end of the talk, we'll invite people to ask questions by raising their hand. You can do that by going to the participants list on the right-hand side of Zoom and hitting the raise hand button. Also, people can use, see several people have found the chat button at the bottom. And if you can't do the raise hand thing or prefer to just have a written question, you can use the chat and I'll try to follow those as well. So without further ado, we will get started. I also want to remind people that this talk is being recorded. And as I mentioned, the recording will go on YouTube shortly. So please take it away, Andre.
All right, so hopefully everybody can hear me and everybody can see my slides and everybody can see this little hand here, which I'll try to use as a pointer. So thanks everybody for coming. I don't know how this is going to work out. I don't know how to give these remote talks, and I hope you don't know how to listen to them, so we'll be new at this together. But I'll get started. So first of all, let me just thank the Aspen Center for Physics for the invitation to give this talk. It's a shame I can't be there, but I'm there in spirit. So let me get started. So my job is to tell you something about particle physics. And what I want to do is to concentrate on some very simple things about particle physics that we figured out over the last couple of decades that we don't understand. So this is a little summary of what I want to talk about. I want to remind you very briefly of what particle physics is about. And then I want to describe for you 3 things that we haven't understood yet. And they have different names. I'll talk about neutrinos most of the time. And then after that, I'll talk about what's called the dark matter puzzle. And then at the very end, I'll try to ask another weird question that particle physics people like to ask, which is, how come the universe has so much stuff in it? And again, my goal in this talk is not to tell you what we think the answers are, but I want to try to give you a sense of what the questions are, because I think these are interesting, relatively basic questions, and they are the things that get a lot of particle physicists excited. So that's kind of the goal for this talk. So very briefly, what's particle physics about? So if you wanted to summarize it in one slide, which I try to do here, is you know, humanity has been in this very, very long road of asking what are things made of. This is a very old question, and we've made an immense amount of progress over the last 2,000 years. And particle physics is the flag bearers of that. So we want to ask, you know, are there basic building blocks for everything? And we think the answer is yes. We think that these things are particles. And then, of course, you're not just happy identifying what the building blocks are. We want to try to describe them as much as possible and how they talk to one another. If you wanted to ask a different question, you know, we're in the business of finding out, you know, what are the fundamental laws of nature that in principle govern all natural phenomena. We're very far away from getting there. There's some big holes in our understanding, and I won't be talking about big theoretical holes, but I want to talk about more pragmatic things. And of course, you know, once you understand particle physics, there are many open questions in science that we can actually answer. And they're very simple questions, or simple questions to ask, you know, like how do stars work? How come we have all these different nuclei, but we don't have more nuclei? And all kinds of other things, which are questions you can ask once you learn a little bit of science. And it turns out that particle physics plays a role in answering those questions. So going back to stuff that you're probably familiar with, this is a picture of the periodic table of elements. It was constructed, in the 1800s, and we added a bunch of pieces. And for a while, this was our understanding of particle physics. We had all these atoms that were the particles, and everything was made out of these things. And then as we learned more and more, we found out that those particles or those atoms are made out of other stuff. And we broke that apart, and then we found out what that's made of. And we've gone beyond this very beautiful but very complicated table to something which is the more modern analog of that, which is something that looks like this. If you follow particle physics, you probably have seen charts like this before. This is our particle physics periodic table. So all of the fundamental particles are here. If you didn't know, this is what they look like if you get really close. And they fall into different categories. We have what are called the matter particles, which are on the left-hand side, and the force particles, which are on the right-hand side. There's a new addition to this table, which is the Higgs boson. And all of these particles are our fundamental particles. And we're very good at describing how they talk to one another. So this is what particle physics is about. This is our periodic table. And our hope is that by understanding all the properties of these particles and how they talk to one another, we fulfill our job. I want to give you a sense of how particle physics works, or how we work on the daily life. And I want to do that by using an analogy that's due to Einstein, which is very old, but it's still quite nice. I think Einstein said that the job of physics is to describe nature. And he said, nature is sort of like a clock, and we humans get to learn certain things about the clock. So for example, we see the hands of the clock moving, and we figure out that the clock has 2 or 3 hands. And by looking at how the hands are moving, we try to figure out how the clock works. Okay, what I have here is a picture of a clock. And our clock is transparent, which would be super nice, because if you have a transparent clock, you can get a hint of what the gears are. And that's sort of one thing that we do to study particle physics, is we study nature, and we observe natural phenomena as much as possible. And then nature's telling us how little bits and pieces of nature work, and we try to put everything together. That's one way of studying nature. There's another way, which is also very common in particle physics, which is we can do better than just stare at the clock. One thing we can do is we can take one piece of the clock, like a little gear here. And then what we do is we try to measure everything that we can about this gear as much as we can. And then we go to the next gear, and then we measure other properties of that. And then we figure out that one gear can, interact with the other gear, and so on. And the hope is that by understanding what all the pieces of the clock look like, we get some sense of how nature works. A lot of particle physics is like that. So whenever you hear people saying that they're precisely measuring the properties of electrons or neutrinos or muons or other fundamental particles, that's the kind of way of doing particle physics that people are actually pursuing. It turns out that there's a third way, which is not what I'll be talking about a lot, but it's the way that people normally think about particle physics, which is we can do better. So one way of studying our clock, which is nature, is that we can take the clock and we can hit it really hard. And if you do that, pieces of the clock come flying out. So another way of studying how nature works, or what things are made of, is by effectively throwing them at the wall and looking at the bits and pieces that come out, and then hope that we're learning about what the clock is. And that's kind of how collider physics works. So we take protons, we smash them against each other, and we try to get a sense of what comes out, and hopefully that will teach us how these clocks work. Again, it's a violent thing, so I'm not going to be talking about violent things today. I want to talk about neutrinos. So let me jump right into that. So neutrinos are fundamental particles. So they live over here in this picture. There are these smiling masked figures in the middle of the table here. And they are part of this zoo of fundamental particles. The reason I want to talk about neutrinos is that they're very hard to study, which means that it took us a long time to figure out that they existed. And it's taking us a super long time to measure the properties of neutrinos well. I do want to tell you a little bit about what the neutrinos are and why they're kind of a big deal, even if you don't care about particle physics. And the reason is that it turns out neutrinos are absolutely everywhere. And the best example that people like to talk about is the sun. So as you know, the sun is this big star that sits relatively nearby and produces a lot of light. And it turns out that as the sun produces a lot of light, it also produces a lot of neutrinos. If you could calculate the flux of neutrinos coming from the sun, the numbers that we like to talk about is that there's about 100 billion neutrinos traversing your finger every second right now, and all the time. So these neutrinos are here, and they are going through you like crazy. Neutrinos are also produced in our atmosphere. They are produced in huge numbers in the Earth's crust. They're also produced in nuclear reactors in abundance. So neutrinos are not some hard to find particle. They're literally everywhere. They're also produced very far away. This is a picture of a supernova explosion in a nearby galaxy. And the way that you want to look at this is there's this little point here, which with the arrow indicating, this is before the supernova went off. And this big bright thing is what happened, what it looked like when the supernova went off. It's a very catastrophic event when the star explodes like that. It's a relatively rare event. And the thing that's absolutely crazy is that if we could take a snapshot of this using neutrinos, the brightness would be about 100 times brighter. So basically, this supernova explosion is mostly a neutrino explosion. And finally, the last thing, which I will come back to, is it turns out that neutrinos were also produced when the universe was born. And they didn't go anywhere, so they're actually here. So these primordial neutrinos are also everywhere. There's a few hundred of them in every cubic centimeter of the universe. So how come it took us such a long time to find a particle that's everywhere? The reason is that they're actually incredibly hard to see, which is why you don't get to feel all of these neutrinos. That's relatively easy to understand. They're called neutrinos because they don't have any charge. And it turns out that they also don't suffer what's called a strong nuclear force. And it turns out then that neutrinos only interact via what's called the weak force. And the weak force, it turns out, is very weak, which is why it's called the weak force. So to give you a sense, I told you that the sun produces a gigantic amount of neutrinos. But if you wanted to shield the universe from all of these neutrinos that are producing in the sun, you could do that. But in order to do that properly, you would have to surround the sun with a ball of lead, which has about the thickness of the solar system. So if you did that, you could make sure that the sun is not emitting any neutrinos that are harming other stars elsewhere. So that's just to give you a sense of how difficult it is to study neutrinos. And you're allowed to ask, okay, so if they're so hard to study, how come we know anything about them? And the reason is, as I said, there are lots of them. And we know how to make really big detectors. And one number that's very useful to keep in mind is, so remember I said that there are these neutrinos from the sun that are going through you all of the time. So you can ask yourself, how likely is it that a neutrino will actually hit you? And the answer is, if you live long enough, you probably get hit by one of these neutrinos in your lifetime. So if you're lucky, or unlucky, depending on how you look at it, one neutrino from the sun will hit you in your lifetime. It's something to keep in mind. That means if you were bigger, if you were 100 times bigger, you would get hit by a neutrino once a year. And if you were way bigger than that, you could be hit by a neutrino 100 times a year. So that's what our detectors are. I'm not going to be talking about this very much or at all, but I want to give you a sense of what I mean by having big detectors. This is a picture of the construction of what's called the Super Kamiokande detector in Japan. That's a very, very big swimming pool with water in it, surrounded by detectors. And the swimming pool is the detector. And what you see here, there's a little life raft here. And then there's some people with hard hats. These are real people. And they're going around cleaning the detector, which has a very, very large number of these photomultiplier tubes, which are about this big. So it's a gigantic detector that gets to see, hundreds of neutrinos coming from the sun per year. So that's how we do it, our experiments. So I don't want to dwell on this picture too much, but I want to say that, and this is the message that I want to give people, is so we've learned about neutrinos as a function of time. If I go back to this picture, you notice that there are 3 of them. So we've learned that there are 3 of them. As I said, they only talk via these so-called weak interactions. So that's good. And then there's a few other things that we know about neutrinos. And the thing that I want to concentrate on is until relatively recently, as in the last century, we thought that the neutrino masses were exactly 0. And that's the story that I want to say a little bit more about, which is it turns out that something happened at the turn of the century. And what happened at the turn of the century is that we discovered that neutrino masses are not 0. This is a very difficult discovery. It's a very indirect discovery because it turns out, as I'll try to convey, neutrinos turn out to be ridiculously light, even though they're not massless. They are very, very light, and I'll try to quantify that. So the way that we had to discover that neutrino masses are not 0 was by using quantum mechanics and getting lucky. And it took us a very long time to find out that these masses are not 0. And part of the reason for that is that we were doing the wrong experiment. Basically, in order for us to see the effect of a non-zero neutrino mass, we need to allow the neutrinos enough time to tell us that they have mass. And it turns out that for the most part, we were doing experiments where we weren't giving the neutrinos enough time. Okay, so that's the summary of everything that I want to say about that, and people can ask me questions. I do want to show a really nice picture, which of course I'm not going to tell you anything about what this picture means, but I just want to give you the sense of measuring the property of a neutrino as a function of time. So here, if you want to stare at this, basically we're asking a question of the neutrino and we're getting an answer as a function of the neutrino proper time. So basically, if we ask a question of the neutrino and we don't wait very long, we get this answer. If we wait a little bit longer in the neutrino proper time, we get a different answer. If we wait a little bit longer, we get yet another answer. And if we wait a little bit longer, we get a different answer, and so on. The reason I'm showing you this is to give you a sense of what does pictures like this have anything to do with neutrino masses. And what this picture is telling us is that if you ask the neutrino a question, you get a different answer depending on how much time the neutrino has to think about what the answer is. What this means for us is that the neutrino has an internal clock. And it turns out, if you've learned about, say, a special relativity, which is this theory that Einstein came up with a little over 100 years ago, particles that don't have any mass don't have an internal clock. They don't know how to tell time. Everything for them is instantaneous. So the fact that we could see a phenomenon where the neutrino was telling us that it knows what time it is was an indication that neutrinos have mass. Okay, so that's the big discovery. Neutrinos have mass. And what I want to do for the next 5 minutes is to explain why that's important. Okay, and instead of talking about this picture here, which is not very illuminating, I do want to convey that all the other particles have mass, except for a couple of other ones, except for the photon, which is the particle of light. And we're very happy about that. That's kind of a big deal for us, that the photon doesn't have any mass. All the other particles that we know about have mass. But so why is neutrinos having mass different? And why are people so excited about that? You know, why are your particle physics friends excited about the fact that neutrinos have mass? And I want to say that in 2 different ways. One message I want to try to drive home is that even though the neutrinos have a mass, they have a ridiculously small mass. And I want to try to quantify that. You know, every time you say something is big or small, it is big or small relative to something else. And I want to go back to this picture. So this again is this, and I'll show this picture lots of times. This is our periodic table of particle physics. And again, here are our particles. And I try to give you a sense of how heavy the different particles are. The heaviest particle by far is the top quark. So if you take the heaviest living thing that ever existed, which is an animal, plants don't count, and you assign that the mass of the top quark to make an analogy, that's actually a blue whale. So let's imagine, for the sake of argument, that the top quark is the heaviest possible thing that ever lived, which is a blue whale. I looked this up, so it's actually true. Then you can ask, what are the masses of the other things? So for example, there's something called a bottom quark. It's actually super heavy. So the bottom quark mass is way lighter than the top quark mass, but it's about the mass of an elephant. Okay, so again, just to give you a sense. So if we go down this table and we ask about other particles, there's something called a muon. A muon is like an electron, except it's heavier. And if the top quark is a blue whale, then the muon is like a tiger. So the mass of the muon is the equivalent of the mass of a tiger, which is pretty heavy, but it's way lighter than the blue whale and it's way lighter than the elephant. And then of course the electron, which is one particle that everybody knows about. In these units, the electron is super light. The mass of the electron is about the mass of a small rabbit. And I mean a very small rabbit in these units here. So you notice that the masses of these particles, even though they're all fundamental particles, are very, very different. You know, they range all the way from something like a blue whale down to a small rabbit or a small cat, if you like cats better than rabbits. So you're allowed to ask, okay, so now we've measured the masses of neutrinos. What are those masses like? And in those units, the masses of neutrinos are like fruit flies. Okay, so neutrino masses are that different. You know, if you're starting to make that analogy, in this world here where you associate particle masses to masses of animals, all of the other particles are sort of like mammals, and the neutrinos are not even vertebrate. Okay, so that's how different neutrino masses are. So that's really weird, and that's part of the reason we get super excited. There's another reason we get very excited, which is more technical, but I do want to say that, which is, you know, again, I've been showing this picture many times. This is not just a pretty picture. It's actually a representation of a very powerful mathematical model. And it's taken us a very long time to get here. It is the result of a lot of experimental effort and theoretical effort. We use a framework, which is the best theory we can write down, that knows about both quantum mechanics and special relativity, which we call a relativistic quantum field theory. And it turns out that these theories are very, very picky. That means that once you define what is in the theory, so if you define what are the ingredients of your theory, and then you define what are the rules of your theory, so once you know those things, then the theory is completely determined, except for a handful of things you have to measure. So there are a few free parameters you have to measure, but there aren't too many choices about things that you can do with your theory. So the reason I want to say that is the following. If you take all of the ingredients of our model, so all of the particles that we know about, and if you take all of the rules that we know about, we can actually predict what the neutrino mass is. And the answer is exactly 0. It's a super hardcore prediction. It's not a hard prediction to make. And the fact that the neutrino masses are not 0 means that there's something that we don't know. There's something missing in our understanding of particle physics. Maybe there's some ingredient missing, or maybe there's some rule missing that we haven't run into. So that's why people get super excited about neutrino masses. We have no idea what these ingredients are. I think we can say on the flip side that we know what they could be. So there's a lot of totally different choices for what are the missing ingredients in the standard model. And they all work because we're pretty smart. We know how to build models that work, but we don't know what the right answer is. And in order to get the right answer, we're going to need more experiments. We need more information. So again, the summary of this part of the talk is we've learned something that we know that our model predicted that's wrong. And we know that we need more particles to explain that, but we don't know what those particles are. Okay, I'm going to change gears completely. And I want to talk about dark matter. So this picture has nothing to do with anything except that that supernova that I showed you comes from this galaxy here, which is a nearby satellite galaxy to our Milky Way. And there's a bunch of other so-called dwarf galaxies. And the reason I'm showing this picture is that it turns out that it's a very dark picture. And if we could see what's called the dark matter, it would be a completely different picture. That's what I'm going to tell you about. And again, my job is to tell you questions and not to tell you answers. And I'm going to not talk about this too much. There's going to be a lecture next month by Lisa Randall, and she will talk about dark matter, and she will do a great job. So you're going to learn everything about dark matter from her. Basically, to summarize the story, every time we study a big system in the universe, we do that by looking at what we can see, and we can calculate a bunch of stuff by using the laws of gravity. So we can do that, and by using the laws of gravity and looking at the stuff that we can see, it turns out that if you look at something that's big enough, we always guess wrong how much matter there is somewhere. Okay, so this is a very, 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 very old problem. It started out, it was first pointed out, I think, by Zwicky in 1933. And what he was studying was what's called a cluster of galaxies, the Coma cluster. And basically what you're doing is you have a bunch of galaxies, they're moving around, and you can measure their velocities as they're moving around. By using the laws of gravity and by measuring how fast they're moving, you can guess how much mass is supposed to be there. And if you do that measurement, the amount of mass that's supposed to be there is way more than you had anticipated. Okay, so that's how this was discovered. And it was this person who also came up with the name dark matter, because there's a lot of stuff that we don't get to see, but it seems to be there because that's what gravity is telling us. There's a very famous story. This is a technique for measuring the mass of galaxies pioneered by Vera Rubin several decades ago. And the idea is very simple. If you look at a galaxy, you can look at the velocity of stars that are going around the galaxy. And by measuring the velocity of that star going around the galaxy, you can infer the amount of mass that's on the inside. This is a high school physics problem that hopefully some of you remember. But to make a long story short, if you look at everything that we can see in the galaxy, we expect a curve that looks like this dotted curve here. And when we go out and we make a measurement, we get something that looks like these points, which is completely different from this dashed line over here. So that's a problem. We can make up for that by pretending that our galaxy or galaxies live inside a big invisible halo of stuff, which is way bigger than the visible galaxy. And the contribution of that are these dashed dotted line. And that explains the data. But the price you pay for that, or the discovery you make, is that there's a lot of stuff that we don't see. Okay, and that's this thing that, again, we refer to as the dark matter. So there's a lot of stuff that we don't get to see. I'm not going to talk about this because I don't want to make the talk too long, but here's another evidence for this thing called the dark matter at a bigger scale. I do want to show this picture because it's a really cool picture. We have other ways of inferring the masses of things, like clusters of galaxies. So here's a way of measuring the mass of a cluster of galaxy. And this is a complicated picture. It has a bunch of peaks in it, all this structure here. Every one of these peaks is a galaxy. That's really boring. We don't care about that. What we care about is this smooth, very, very prominent background that the galaxies are living in. That is matter that we don't get to see. That's the dark matter. And there's a lot of it. There's a lot of mass in the galaxies, but there's a lot of mass in between the galaxies that we don't get to see, and that's also the dark matter. I'm also going to skip this. So why do particle physicists have anything to do with this dark matter question? The answer is the following. Okay, so we know that there's a lot of matter that we can't see. So we ask, so what is it? And we've tried to get the answer to that for a very, very long time. And we've concluded that we're very, very sure what the dark matter is not. And the dark matter is not made out of any of these things that live in the standard model of particle physics, as far as we can tell. For a while, people were excited that maybe the neutrinos were the dark matter. That's not true. Maybe the dark matter was made out of planets that we don't get to see or stars that don't shine. That's also not the case. So it's complicated. So we know that there's a lot of this dark matter out there. And we know what the dark matter is not. And the dark matter is not made out of regular particles that we know about. That's sort of a big embarrassment, because remember, our job as particle physicists is to explain what everything in the universe is made of. And it turns out that there's a lot of mass in the universe that is not made out of any of these particles here. That's kind of what I wrote down here. And again, the challenge is we know what the dark matter is not. And because our job is to do particle physics, we think that that means that there's some new particle. It's not any of those particles that were here. So it's some new one. And then we can start asking, so what do we know about this thing that is the dark matter? And basically, we know lots of properties that the dark matter doesn't have. It doesn't have electric charge. It doesn't participate in the strong nuclear force. Probably. We don't know, but it's very likely. Actually, it doesn't seem to interact very much at all, because otherwise we would know about it. And of course, it probably lives very long because it's still around. So that's what we know about the dark matter. I do want to point out that it kind of looks like a neutrino. It doesn't have any charge. It doesn't interact via the nuclear force. It doesn't interact very much at all, but it's not a neutrino. But it could be a friend, and that's a theme that I'll talk about in a minute. I do want to show this picture because it's a really nice picture. And everything that I said in this slide is everything that we know the dark matter doesn't have. It doesn't have charge. It doesn't decay. It doesn't interact very much. But you can ask other questions. Okay, so what's the mass of this thing? And the answer is we have absolutely no idea. Zero idea. We have no idea at all. So here's a plot of all the possible masses the dark matter could have. By the way, if you're an enthusiast of bounds, we know that it can't be smaller than this ridiculously small number here, 10 to the minus 20 in some units. You know 10 to the minus 20 is very small. And so it could be anywhere between 10 to the minus 20 in these units and 10 to the 70 in the same units. And by the time you get here, the dark matter is made out of black holes. And almost everything in between is allowed. Now there's this heart over here, and that indicates one place where we've been spending a lot of time looking for dark matter. And we haven't found it yet, but we haven't given up. I do want to say that if you follow the newspaper, there's some excitement about a new form of matter called axions. It could have something to do with the dark matter. I'm not going to say anything about that, except that it's here in this picture. It kind of lives here. There's a very serious gentleman over here. That's Mr. Planck. And this here is to indicate what the heaviest possible fundamental particle mass could be, which is around over here. So if you're on the right side of this plot, we're not talking about fundamental particles anymore. We're talking about black holes or things which are big. So that's all I wanted to say about the dark matter. Okay. So the last thing I want to talk about for maybe 5 minutes is the very last question that I think we can ask, which is a very big question. And it goes by a complicated name called baryogenesis. Or if we translate it into words, we're interested in asking how come there's so much matter in the universe today? Okay, and again, my job is to explain to you what the question is, and I'm not going to tell you what the answer is because we don't know what the answer is. So let me show you this plot on the right-hand side. And this plot here is a plot of how many particles there are of a certain type on average in the universe. If you look here, I mentioned the neutrinos and the photons. There's a few hundred of those per cubic centimeter in the universe on average everywhere. This is a picture of these photons that were produced a very long time ago. It's called the cosmic microwave background. And the regular matter is all the way down here. Basically, the average number of protons in the universe, that's about 1 per cubic meter. So you want to compare, 100 per cubic centimeter. So there's 100 photons in a cubic centimeter. And then there's 1 proton per cubic meter. So the number of protons and electrons and neutrons, forget about the dark matter, we don't know what that is super tiny. So how did that happen? And by the way, in this picture, there are no antimatter particles. So the number of antimatter particles would be all the way off the chart by many orders of magnitude. We don't think there's any primordial antimatter in the universe. So how did we get here? And it turns out we do know what the answer is qualitatively. The answer is the following. So in the remote past, the universe was very dense and very hot. So the best way of describing that, it's sort of like a big soup of matter, electrons, quarks, etc., antimatter, positrons, antiquarks, etc., neutrinos, antineutrinos, and photons. And the universe was so hot that these things were in equilibrium. So early on, all their numbers were the same. You had the same number of photons, the same number of protons, the same number of electrons. And then the universe started cooling down. As the universe cools down, the matter and the antimatter start to annihilate into photons. So they start to disappear. So every matter particle finds an antimatter particle, they annihilate. And if you keep running the movie forwards, even though you start out with the same numbers of everything, you end up with just neutrinos and photons. That's what we think should happen. Actually, we can do better than that. We can do a calculation, and we can calculate how many protons would be left over out of this story. The answer is not 0, but it turns out that the answer is off from this number by about a factor of 1 billion. Okay, so even though we do a good job of understanding what's going on, if we predict how many protons the universe has, we get an answer that's wrong by about a factor of 1 billion. So clearly we're doing something very wrong. And of course, there's no antimatter. This is kind of a big deal. It means that we're missing out some ingredient of the early universe. And that ingredient is allowing this annihilation of matter with antimatter to be imperfect. That somehow there was a little bit more matter than antimatter. And then at the end of the day, all the antimatter disappeared because it annihilated with the matter, and we're left off with a little bit of matter. There's a nice cartoon of that. Basically, early on, for every billion antimatter particles, there was 1,000,000,001 matter particle. And then the universe progresses, all the matter and the antimatter annihilate. We're left with this 1 part in 1,000,000,000 of matter. And that's everything that we see in the universe. All of the stars, all of the planets, all of the plants, all of the people, all of the animals, everything is a consequence of this tiny asymmetry between matter and antimatter in the early universe. So how can that happen? And again, the reason this turns out to be a particle physics question is because we're pretty sure that early on, the amount of matter and antimatter was the same. If it was not the same, we're missing out some other bit of information, and people can ask me about that later. So here's one way of explaining how this works. Imagine that there's a new particle, and that new particle can decay into matter, and it can also decay into antimatter. And imagine that that particle, in the process of decaying into matter and antimatter, actually decays a little bit more into matter than antimatter. So if such a particle existed, and if such a particle was present in the universe very early on, we could start out with a universe that's completely symmetric in the matter-antimatter business. But this particle, as it decays, after all of them are gone, you end up with an imbalance. You have a little bit more matter than antimatter. You run the movie forwards, and you get the universe that we observe today. That's the idea. So the reason this is a particle physics problem is because we need a new particle. Again, that's always the theme here. We have no idea what this particle is. We can also stipulate what properties it should have. And the only thing I want to say is that in the end, it turns out that this particle also kind of smells like a neutrino. And just to come back around, one thing people get super excited about is that, so remember I told you We need some new ingredient to explain why neutrino masses are not zero. We also need some new ingredient to explain why the universe has any stuff in it. And it turns out that it could be that the same new ingredient can do both things, which sounds super exciting. So if you believe that, you can start making some predictions. And the predictions are very interesting. So for example, if you believe this idea, which is called the seesaw mechanism, it's just a cool name. And here's a cool picture of a seesaw. And that's all I want to say about that. But you can make some predictions. One prediction that you would make, if this idea were correct, is that the neutrino masses would be very small. That's interesting because that turns out to be true. Another prediction you would make is that the neutrinos would know how to distinguish matter from antimatter. That means you could do an experiment, and that experiment would reveal that neutrinos know the difference between matter and antimatter. Particle physicists refer to something called CP violation about this property of matter to tell matter from antimatter. We're trying to figure out if the neutrinos know how to do this, and we have some hints that the answer might be yes. And then there's another prediction that this idea has, which is that there are more neutrinos. Now, they could be super heavy, or they could be super shy. That means that they're even harder to detect than the regular neutrinos. So we don't know if there are any more neutrinos out there or not. Okay, so let me conclude. So again, what I try to do is to tell you what particle physics is about, and to point out that particle physics is living in interesting times. Unfortunately, like us, which are also living in interesting times. Anyway, we've constructed a model for particle physics. It explains almost everything. But there are some really big things that we get the wrong answer. And we don't get it wrong by a little bit, we get it completely wrong. And I try to give you a sense of what are the things we don't understand. One is neutrino masses. Neutrino masses were supposed to be zero, but they're not. So we need to understand how neutrinos get a mass and what that means. And a lot of people think it means something very important. I told you about the dark matter. Most of the matter in the universe appears to not be made out of fundamental particles. So what is it made of? Is it some new particle? And more importantly, or for practical purposes, what is this particle? And we spend a lot of time trying to find the answer to that. And finally, another weird question that we can ask, which is a particle physics question, is how come the universe has so much stuff in it? If we believe in our model of particle physics, we should have gotten an answer that is off by about 1 billion. So we have some work to do. And this is my last slide. So what are we doing? So we think we know what we have to do. And that colors a lot of what the particle physics people have been talking about for the last several years at least. We want to find out the properties of the neutrinos as well as we can, because they seem to be hiding something. So we're spending a lot of our intellectual resources into learning more about neutrino properties. We want to find what this dark matter particle is. We have very, very little information on that. So we're working like crazy in all kinds of different ways to find out what the dark matter is. And we're looking for more clues. Again, what makes this period of particle physics interesting is that, and I'll just summarize in 10 seconds, is we know we have found lots of interesting things, but we don't know what those things are yet. So it's kind of like making a huge discovery, but you have no idea what you've discovered. So our job for the next, hopefully not too long, is to try to follow up on these discoveries and end up with a deeper understanding of nature. So let me stop here. Thank you.
Thank you, Andre, for a great talk. I want to ask people, we can all virtually clap, and want to ask people interested in asking questions to please use the raise hand button on the, should be on the right-hand side. Chat is possible, but I think we'd prefer people to raise their hands, and then I'll unmute you to ask a question. So I see just one hand raised. So while people are raising hands, I want to just take the chair's prerogative and ask you, Andre, about, since I come from Fermilab, I have to ask you, how would you measure, say, this, you talked about possibility of CP violation in neutrinos. So what kind of experiments would you construct to, it's a leading question.
Yeah, so that's a great question. And basically the experiment we're doing is the following, is we produce a beam of neutrinos, and we ask a question of this beam of neutrinos. And then we produce a beam of antineutrinos, and then we ask the same question. And if we get answers that are related to one another, then neutrinos and antineutrinos behave the same, which means that they can't tell matter from antimatter. But if they give you different answers, then the neutrinos can tell matter from antimatter. In more detail, what we're measuring is neutrino oscillations. And neutrino oscillations are, we can calculate what's the probability of producing a neutrino of one type here and detecting it as a different type over here. So that's the experiment we want to do. So we want to do this experiment with neutrinos, and then we want to do the same experiment with antineutrinos. And then we want to ask what those probabilities are. And then we want to compare and see if the answers that we get are the same. Now the challenge is, in order to do this experiment, you have to put a detector very far away from where you're producing the neutrinos. And very far away is really very far away. It's in, we're building this thing called the Dune experiment that produces neutrinos at Fermilab, which is nearby, about 50 kilometers from here, where I am. It's literally that way. And then we shoot these neutrinos to a different state. In particular, they go to South Dakota. And we need all of that distance in order to give the neutrinos an opportunity to tell us if neutrinos and antineutrinos have exactly the same properties, or if the properties are a little bit different. And if they're a little bit different, then we think we're in the right direction for telling the story that I gave you a snapshot of.
Great, thank you. Actually, Fermilab's that way.
Okay, there you
go. So I see a few hands raised now. So the first one is Ri Zhang, so I'm going to unmute you. I can.
Yes.
Go ahead.
Thank you, Professor, for the wonderful talk. It updated my knowledge in particle physics, like I got 20 years ago. So I have a bunch of questions, but I probably want to ask only two of them. The first one is regarding to the first part you talked about, the neutrino mass problem. And as you mentioned that because the neutrino may have mass, it suggests new particles that haven't been included in the standard model. And my question is, I'm sure there's a lot of candidates for this theoretically, like from supersymmetry or superstring, whatever. But my question is, from the experimental point of view, what is the time scale? Like you're thinking, like what kind of experiment that can be done in how much time and for how long to kind of nail down this new particle for us to decide which theory is right, which theory is wrong, or maybe we need to wait for a long time, because of the money issue or because of the other constraints. So that's my first question. My second question is regarding to the dark matter. Is this possible just to say there's a tons of black holes in there in the galaxy so that we don't see them because they're black and that's it? And what's wrong with that simple explanation instead of trying to find out some other candidates for the dark matter?
Right. So I can say something about the second question very quickly. It's a great question. People have asked this question. Why isn't the dark matter just a bunch of black holes? There's some holes in the question, which is we don't know how these black holes came about. But let's put that aside and ask the question: are these particles just black holes? And it turns out the jury is still out, but it is unlikely that all of the dark matter can be made out of black holes. And the reason is, if it were made out of black holes, we would know about it. So black holes that are super big, we would know about them by doing different kinds of lensing experiments. That means, lensing means that you kind of look for a star that's very far away, and then you wait for a dark matter particle to go in between you and the star. So if that happens, the brightness of the star will change. So we've been doing those experiments for a while, and that means we haven't seen this phenomenon in large quantities, so we can rule out very big objects as the dark matter. And then there are other ways of constraining very big things. So my understanding is that it is very unlikely that very big objects can be all of the dark matter. They could be some of the dark matter, and people still get excited about this, especially with these discoveries of gravitational waves from black hole collisions. We don't really understand how these black holes come about. So there's some careful pursuit of that that's going on. So let me say something about your other question. And so the answer is, so we know that neutrino masses are evidence of some new particle. That's the message. The question is, what is this new particle? And the answer is, there are lots of different choices. And depending on what the right answer is, the way for finding this new particle experimentally is completely different. We could find this new particle by doing these neutrino oscillation experiments. Maybe we can get some evidence of this particle by doing precision measurements of the universe and the kind of stuff that Josh works on. Or we can find this new particle in a collider experiment, or we can find this new particle by studying rare muon processes. So, and again, I'm just listing random things because we really don't know what this particle is. We know what it could be, but what it could be is very, very diverse. So it is possible that we will learn more about the origin of neutrino masses very soon, like in a few years, but it's also possible we won't learn about it for a very, very long time. And that all depends on how kind nature is to us. Does nature want us to find out why neutrinos have mass, or does nature not particularly care about us? And it is possible that the mechanism behind neutrino masses will be very difficult to reveal. The key point is we have no idea what the answer is. We know lots of different things we can look for, and that's our job. Our job is to look for these things and see what happens. And that's the best that we can say for now, because we're missing a lot of information. So
thank you very much.
That helps.
So
thank you.
we've got a few more questions. I'm going to just remind people we're getting to the bottom of the hour. I think with Andre's patience, we'll go a few minutes over the hour to enable a few more questions. So the next one is by Adam. And I need to unmute. There you go.
Thank you very much for the presentation. It was wonderful. My question is about the particles that smell like neutrinos, dark matter candidates, and N that you mentioned in baryogenesis. Aside from gravitational charge, mass, and not much else interaction, along with a possible CP violation, are there any other properties that make these candidates smell like neutrinos?
Yeah, that's a good question. And when I say that they smell like neutrinos, that's almost as much as we know, but we do know a little bit more. And basically the way that we ask this question is the following. Imagine that I invent some new particle. And I know that this new particle must have dark matter-like properties. So if I do that, I can then start asking, okay, so now that I've invented a new particle that doesn't have any charge, doesn't talk to the strong nuclear force, what could it talk to? And it turns out that among the very few things it could talk to are neutrinos, because the neutrinos are also neutral. So it's not outside the realm of easy possibilities that every time you invent a new particle that doesn't have any charge, doesn't have any color, if that particle chooses to speak to the particles that we know about, it oftentimes will learn how to speak to neutrinos, but will have a very hard time speaking to anybody else. So it's in that sense, because they share these very simple properties, they have an opportunity to interact with our particles. They have a harder time talking to electrons or quarks or gluons and stuff like that. That's what I mean. And if you write down concrete models, this is much more explicit. And again, I want to emphasize, none of this has to be true. but a lot of this is suspicious. And one thing which I like to say, which is very common to particle physics, is that every time you have more than one problem, we always try to think about, is there a way of solving all of these problems at once? And that's sort of, and again, there's no reason for that to be true, but people like to be economical. So that's something that humans appear to be capable of doing very well, which is to find similarities in the things that you don't understand. Again, the short answer is we don't know, but it is suspicious. And again, 10 years from now, this could be all completely wrong.
Thank you very much.
Okay, the next question is from Bill.
Hi, Andre. Thank you for the talk. I had a simple question. You cut out a little bit, but it sounded like you were saying there might be a fourth neutrino. Is that right?
So I said lots of things, and what I said was, in this economical scenario where you explain neutrino masses together with the origin of this matter-antimatter asymmetry, one of the predictions that you make is that there are more neutrinos out there.
So if there are more neutrinos, let's say a fourth one, does that imply that there's a fourth particle lepton with charge? And if so, why haven't we seen that?
Yeah, that's an excellent question. And the answer is there better not be, because we would have seen it by now. So these neutrinos are special. These are neutrinos that don't come along with what's called a charged lepton.
So there's nothing in the standard model or anything that implies that if you have a fourth neutrino, you need a partner.
That is correct. So the story goes that if you look at these particles, we like to stack them together that way, and that's not by accident. So every time there's a regular neutrino, it better come along with a charged lepton, some particle with charge. So if you have more neutrinos, they have to be not of this regular type. So that's why it's so people refer to it as a stereoneutrino or a non-interacting neutrino. So it is something that, again, as I said in the previous question, it is something that knows how to talk to neutrinos. So we abuse the name and we call them neutrinos as well, but they can't just be a vanilla neutrino like the neutrinos that we know about. They have to be a different kind of neutrino. Because as you say correctly, if they came along with some other charged particle, we would definitely know about that. That is completely ruled out by experiment. It's not ruled out by theory. Theoretically, we could have done it. It's a little bit messy, but we could have done it. We probably would have had to add some new quarks as well, but that's a different story. But the problem is we've done too many experiments to know that there isn't another electron-like particle that is just like the electron but heavier.
Thanks.
Okay, the next question is from Kenneth.
Yes, I agree. That was a terrific talk. Thanks a lot. So I was wondering, can we sort of frame what you're saying in the following way? That originally we tried to take all the particles that are easy to see and use them to tell the story of the universe. And in that story, we said some stuff about the particles that are really hard to see that we got wrong because we thought they should have no mass. But it sounds to me like you're suggesting that maybe we should try it the other way, to use the particles that we can hardly see at all to tell the story of the particles that we can see. And obviously, if you're saying that, it's going to be a big challenge, but I think that's a fascinating way to...
Yeah, and I do want to emphasize that's sort of a last resort. As I said, we really don't like to invent new particles. We only do it because we have to. And at least that should be the way people operate. And again, in the case of the dark matter, for example, we tried very, very hard to ask if the dark matter could be made out of regular particles. So we tried all the different possibilities. And again, when I started off in graduate school, it was a logical possibility that the dark matter was neutrinos. That turns out to be wrong, but we definitely asked if that was true. Just like I said, we also asked, maybe the dark matter is just a bunch of stars that don't shine anymore, failed stars, black holes, planets. We look for that, we don't see it. So it's not like we want to invent a bunch of new particles. We're being pushed towards inventing new particles. So I don't know if that, I hope that that's helpful.
Sure, yeah.
Okay, I think our last question of the evening is from Roger. Let me.
Unmuted. I was just curious for your experiment that, if I understand it, you're showing that the neutrino properties, such as mass, that it can be detected, varies over time. And is there any way to know that, the implication is that it's just each single muon has its own variation. But is there any way to know or measure or suggest that all neutrinos, in a given space or localized area are in any kind of synchronization or being affected simultaneously by some other particle interaction?
Yeah, so let me try to clarify one thing. It's not the neutrino, none of the neutrino properties are changing. It's just the answer to some question. So the question we're asking the neutrino is, so we produce it in some flavor, like the electron neutrino. And then later on, we ask, what's the probability that that will be detected also as an electron neutrino? That's the thing that's changing with time. And because it has time dependency to it, we can infer that the mass of the neutrino is not zero. So that's not the topic that I chose to cover, because it's a fascinating but very long story. So basically, I just wanted to make the point that we haven't measured the masses directly because they're so small, but we have to infer them from these so-called oscillation experiments. So I do want to make that clear, and I lost what the other part of the question was.
That's okay. Well, I was just trying to figure out if there were, or understand if it was a singular measurement sort of associated with a given neutrino, or if the effect of the measurement could be applied to all neutrinos in a given space.
Yeah, okay, so that's
time in the oscillation.
Yeah, I can add a little bit to that. I think we have done enough of these oscillation experiments to infer very robustly that that the neutrino has a mass, just like all of the, so all of the electrons have one mass, regardless of where they live, and it's all the same mass. That, by the way, is one of these big, weird questions in particle physics, but it's true. So every single electron everywhere in the universe has exactly the same mass. So every single neutrino of a certain species everywhere in the universe also has exactly the same mass. And we have done enough measurements to be relatively confident that that statement is correct. If it were not true, it would be really weird.
Okay, thanks.
Mm-hmm.
Okay, I think we're going to have to call it an evening. Really want to thank Andre again for a wonderful talk. I want to thank everyone for joining this evening in this experiment. I think it was wonderful, different kind of interaction. We had over 140 people at the peak, so that's great. I want to remind you that this is a weekly series that will be continuing through the summer. And you can visit aspenphys.org for more information. And again, next week's speaker is Peter Armitage, speaking on macrocosm in the microcosm, analogies between materials and particle physics. So thank you, Andre. Thank you to the Aspen Center for Physics for hosting this. And the video will be shortly on YouTube. So take a look for that. And hope to see you all in future weeks at these events. Thanks, everyone.
All right, thank you.